So in this class, we are going to talk about organic and molecules and biological molecules. And so we're going to start with organic molecules and we are going to start with alkanes. And alkanes, by and far, are largely unreactive, except they do go through a combustion reaction. And so a common alkane, for example, would be propane. This is a image of a propane torch. We also find a lot of alkanes in crude oil, which then can go on and make a lot of the products that we use, a lot of the plastic products. So we see alkanes quite a bit in our everyday life. Now, before we jump into alkanes, let's define organic chemistry. Now, historically, early chemists thought organic compounds could be produced only through some sort of action of vital force, right? So at the beginning, we had this vital force, which was called vitalism, okay? And again, the idea there was, right, organic compounds could only be active in living organisms. So originally, that the idea there was that something was organic. So before 1828, right, the idea was that you could have something that was organic and that had to be involved in a living organism in some way. And then things that were inorganic was just everything else. So rocks, all of that business, those are inorganic, okay? And so I said before 1928. So what was the big deal about 1928? Well, in 1928, there was a guy that came along and he was named Frederick. There's an I in there, so let's back up. Frederick Wohler, or Wohler. He's German, and he heats an inorganic salt. So this is our inorganic salt. It was ammonia cyanate, not found in living organisms. He heats it up and boom, it produces urea. And this just rocked everybody's world because this is found in blood and urine. And so this was considered an organic compound, right? And it came from something that was inorganic. So this kind of shifted, so this shifted the idea of organic chemistry away from vitalism. And so he discredited that kind of vital force theory, and his success there really prompted other chemists to start organizing, or start synthesizing organic compounds. Now, today, organic compounds are being synthesized in the thousands by laboratories, and most of the things that are being synthesized haven't ever been isolated from natural sources. Now, one of the things that organic compounds share, the one unique feature, is that they all contain carbon. And so when we talk about organic compounds and we talk about organic chemistry, this is the study of carbon containing compounds. Okay. And there are a few exceptions to this. A small number of the carbon compounds, like CO2 and carbonates and cyanides, they sometimes can be classified a little differently. They're as inorganic because they were obtained from non-living systems, and kind of historically we stay with that. So they're still considered inorganic compounds, but mostly. Organic chemistry is the study of carbon-containing compounds. And these include things like glucose, right? We can see that glucose contains lots of carbon. That is a sugar. Testosterone here is a hormone. Lots of carbon here. DNA has lots of carbon as well. And these are some of the biological molecules that we'll study at the end of the semester, where we're really focusing on the biochemistry of these carbon-containing compounds. So when we talk about inorganic compounds, and they were defined as kind of, things that came from non-living things. But now we really define inorganic compounds are everything that doesn't contain carbon. Okay. So, let's compare some properties of these organic and inorganic compounds. So when we look at the properties of organic compounds and inorganic compounds, there's a few things to be aware of, right? One of the things is organic compounds are generally going to undergo covalent bonding, and I just want to remind you that that's just the sharing of electrons, okay? And the forces between these molecules are generally really weak. As opposed to that, inorganic compounds often have ionic bonding. This is where they're held together with electrostatic interactions. So we would see then a positive and a negative charge, and that's super strong. Organic compounds can be gases or liquids. They have low melting point solids. Inorganic compounds are generally high melting point solids. For example, sodium chloride is an inorganic compound, and it's got a really high melting point. Organic compounds are often flammable. Inorganic compounds are generally non-flammable. They're generally not very soluble in water, whereas these inorganic compounds generally are. Organic compounds are not conductors. Inorganic compounds can conduct electricity. Organic compounds generally react pretty slowly, whereas inorganic compounds can react pretty quickly. Now, it's kind of interesting, the subdivision of chemistry into organic and inorganic results in a branch that deals with compounds composed of just mainly one element, right? So again, we are just focused on carbon. That's our bright shining star. And this classification, when we think about the number of organic compounds, this classification tends to make a lot more sense. We have identified approximately 500,000 inorganic compounds, and that's a lot. But when we think about organic compounds, we have more than 9 million organic compounds that have been identified. And we also know that we are synthesizing thousands of new ones, and they're being isolated every year. So that's why we have just one division of chemistry dedicated to the study of carbon. Now, one of the reasons we have really large numbers of organic compounds is that carbon has a really unique ability to form stable covalent compounds or covalent bonds with other carbon atoms and with atoms of other elements. And so the resulting covalently bonded molecules can contain just a few carbons or can contain a lot of carbons. Now, there are two really big reasons for the massive number of organic compounds. One is the bonding characteristics of carbon atoms, which we're going to talk about next. And also, what we're going to end this screencast with is the isomerization of carbon-containing molecules. So when we look at the bonding characteristics here, as a group 14 element, a carbon atom, right, when we look at carbon, it has 4 valence electrons. Now it has 6 electrons total. And I want to remind you that electrons around an atom are organized into shells. Okay, and the shells increase in energy. And what we're going to look at here is just carbon. And carbon has a 1s shell, and this is the closest one to the nucleus. So this is the closest to the nucleus. And then it's got a 2s shell and a 2p shell, and these are the farthest away from the nucleus. When we look at this, if carbon were to have this particular arrangement of electrons, it would only be able to form 2 bonds because it only has 2 unpaired electrons. But in reality, we know that carbon can form 4 bonds. For example, we have the carbon molecule methane here. And so carbon can form 4 bonds. We know this, we can isolate this. And so this theory can explain some properties of molecules, but it couldn't explain the bonding in carbon. And so scientists had to develop a theory that could support the experimental data that we had. So Linus Pauling, who was the winner of the Nobel Prize in Chemistry in 1954, developed a useful model to explain this new bonding characteristic. So Linus Pauling proposed hybrid orbitals. And so basically what he said is, hey, look, we know that carbon makes 4 bonds, okay? And we know that there are 2 electrons in the 2p orbital and 2 electrons in the s orbital. And so what if these guys mixed up and we actually have 4 unpaired electrons that can then make bonds with, for example, in methane, the 4 hydrogens here. And so he said, if we mix all of these together, we have 3 p orbitals here and 1 s orbital here. And so if we mix those up, we have 1 s orbital for every 3p. And so we would call that an sp3 orbital, where we have 1 s orbital and 3 p orbitals that are all mixed together. And that's called a hybrid orbital. So he proposed these hybrid orbitals, which are just orbitals produced from the combination of 2 or more non-equivalent orbitals of an atom. And so let's look at the shape of the hybrid orbitals, because it's showing circular here, but it's not actually circular. And so when we come over to look at orbital shape, an sp3 orbital has, right, a 2-lobed shape, which is similar to a p orbital. So when we look at orbitals, which are where electrons are thought to be around an atom, you can have a p orbital which looks like a lobe just like this. Then you can also have an sp3 hybrid orbital, which is what carbon has, and it's kind of elongated like that. So it's kind of like we mushed that s orbital in there. So when we look at methane here, each carbon-hydrogen bond results from an overlap of a carbon sp3 orbital and the hydrogen 1s orbital. Okay, and so basically what happens is carbon has its big sp3 orbitals, and then hydrogen comes in, and hydrogen just has an s orbital, and they overlap, and that's how they make a bond. Now, This particular bond, right, is called a sigma bond. So the sharing of those two electrons in that overlap region results in a sigma bond. And that's the lowercase Greek letter sigma, and that's what we use to represent that. Now, each of those carbon-hydrogen bonds in methane, right, end up giving us orbitals that point in such a way that we have a tetrahedral shape. So if you remember way back from Introduction to Chemistry 1, when we talked about the molecular geometry, we talk about the molecular geometry of carbon, particularly carbon and methane. It's going to be tetrahedral because we have the central carbon and then we have 1, 2, 3, 4 hydrogens that are surrounding it, and their bond angles are 109.5, and it forms a kind of like a pyramid, which is where we get that tetrahedral from. And so that's the shape we see there. Now there's other ways that we can represent this. I want to remind you that a piece of paper or a computer screen or a tablet, that's going to be 2 dimensions. And so this looks very flat, and it can be very misleading because it looks like these bond angles are 90 degrees, but we know they're not. And so, for example, this is a space filling model where you can see the hydrogens that are bonded to that carbon as well. Now, as I mentioned before, carbon can also make many bonds. So carbon atoms have this ability to bond to other carbon atoms. So carbon atoms can bond with other carbon atoms. Okay? And there's really no limit to the number of carbon atoms that can bond covalently. So it is important to know that each carbon can only make 4 bonds, but lots of those carbons can link together. So for example, if we look at carbons here, you can see that we've got a long chain of carbons. These can also form double and triple bonds. And I want to remind you, double bonds are the sharing of 4 electrons, and triple bonds are the sharing of 6 electrons. So you can have a long chain. You can also have branching because carbon can form those 4 bonds. So a kind of an interesting thing about organic compounds or molecules is they can range from really simple molecules like methane to very complicated molecules with over 1 million carbon atoms. And so to help make this manageable for us, we look for patterns, and that's what organic chemistry is going to be. That's what we're going to focus on. Now, this also results in molecules that have the same chemical formula but different structures, and those are called isomers. So we were talking about isomerization here, and when we discuss this, this is just the property where 2 or more compounds have the same molecular formula but a different arrangement of atoms. Okay? And so when we talk about this, there are lots of different types of isomers, and we'll talk about a lot of different type of isomers. But the first one we're going to introduce are structural isomers. These are also sometimes called constitutional isomers. But your book, so we have lots of synonyms in science, but your book tends to stay with structural isomers. But if you see constitutional isomers out there somewhere, I don't want you to get confused. Those are just synonyms of each other. And so these are going to be isomers, right, where the bonds, where the atoms, let's say that, where the atoms bond in different patterns. Okay, and so a really good example of that is ethyl alcohol and dimethyl ether. And so when we look at both of these molecules and we count the number of carbons, we can see they both have 2 carbons, that would be C2. They both have 6 hydrogens, that would be H6, and they both have 1 oxygen. And so they both have the different formulas. They both have the same formula but different connectivities. And so let's look at an example of how we would use the rules for covalent bonding to determine the structure. And so this is an example in your book. It's example 11.1, and it says use the usual rules for covalent bonding to show that a compound with a molecular formula of C2H6 demonstrates the property of isomerization. So you're going to draw the formula for the isomers and you're going to show all the covalent bonds. And so I just want to review these patterns with you. And the big pattern here is carbon is going to form 4 covalent bonds. Carbon is never going to form 5 bonds. I get to say never in science, and I really love doing that, but it's not going to form 5 bonds for us. Oxygen is going to form 2 covalent bonds. And hydrogen will form only 1 covalent bond. So when you are asked for a structure and to determine the different isomers, my suggestion is to leave hydrogen to last. Okay, and so when we look at this particular example, we've got 6 hydrogens, but what we're really interested in there are carbons and oxygens. And so we can imagine that we would arrange our carbons where they would be attached in this fashion, but we could also arrange our carbon where they would be attached in this fashion. And now what we're going to do is we're going to look at our bonding patterns and we're going to make sure that carbon has 4 bonds and oxygen has 2 bonds by attaching hydrogens. So when we do this, we can attach 3 hydrogens to carbon, and now that carbon's full because it can only make 4 bonds. Then we're going to attach 2 carbons to this hydrogen, and now it's full because it can only make 4 bonds. And then oxygen can make 1 more bond, so we're going to attach a hydrogen there. And when we look at this, we have 2 carbons, 1 oxygen, and 6 hydrogens. Same thing here. The oxygen already has 2 bonds, and so we are going to make sure that carbon then has 4 bonds. So we'll continue to practice this in class, and that ends this screencast. In the next screencast, we are going to look at the different ways, so the different kind of patterns of atoms that we see in organic chemistry and how those gives rise to groups that then will go and react.